So hi everyone. So today's paper just came out. It's called Pre-trained Transformers as Universal Computation Engines. This is a paper I have quite a few friends offline who shared this with me. There's a lot of excitement around it. And so the main idea behind what they did was, so this is a collaboration between some folks at Berkeley and Facebook AI and Google Brain, some just like really top people overall. And they investigated the capability of a transformer pre-trained on natural language processing to generalize to other modalities with minimal fine-tuning. So without fine-tuning the attention, the feed-forward layers of the residual blocks, and they call this model a frozen pre-trained transformer. And so what they did was, so they trained it on language, and then they tested it out on sequence classification tasks, numerical computation, vision, protein fold prediction. So typically, even before when people did this sort of experiment with like language models, like they would train them on the same modality. Like, I mean, if it's trained on language, you would test it on language. There, as far as I know, this is the first work that trains like fine tune something on a separate modality entirely. That said, it does fit into this general trend of this work that's using transformers on like modalities like vision. So, for example, like the vision transformer work, or a clip, or Dolly. These are all examples of uh, like basically getting benefits from training something on and the multimodal neuron work. So I have a video on this. So all of these are examples of when you're training something on language and image data at the same time, you end up with models that seem to understand both, which is very promising. And so here, I guess, like they're sort of making the claim that in fact pre-trained transformers can be used in this way, where you fine tune it one modality and it still generalizes. And this is very interesting because it means it's not memorizing, right? Or it essentially means that it is sort of like understood something about a concept. Specifically, if you were to look at the multimodal neural network work by, again, this is the folks at OpenAI. Um, you as a human, you know that like if you see the word, I don't know, Rihanna, then you recognize the word, but you could also see Rihanna, or you could see the cover of her album, and all of these concepts are going to activate the same parts of your brain. And so this is sort of similar. Like the fact that we have models that can generalize across modalities is again huge. It also explains that you may have seen some news today. So Hugging Face recently raised $40 million in their Series B. This is a very big amount for an ML library, but it's interesting because if you consider that Hugging Face today is pretty much the way in which people use language models, and if language models are universal compute engines, this means that this sort of justifies this 40 million price tag, right? It's sort of saying if all of this innovation around like potential AGI using these techniques is going to happen via Hugging Face, and most people use Hugging Face, that means Hugging Face is worth a lot of money. So just going over the paper here they talk about like the frozen pre-trained transformer. And I guess here, just to be clear, the frozen pre-trained transformer is to distinguish it from the full transformer, as in you fine tune it. And so it looks like here, um, a bit memory, but XOR. Okay, so these are just like examples where, yeah. So this is these are like easy, right? Just memorizing, and then XOR is sort of like you want any neural network to sort of be able to distinguish these things. I know what list ops is. It's very bad though. And so then there's okay, MNIST, Cyfar, okay, and then let's see. So this is in blue, the frozen pre-trained transformer. Seems to do a bit worse than the fully trained one. For some reason, LSTMs are even better. Whereas if you look at Cyfar, for example, like let's say an image data set, then LSTMs don't seem to do a particularly good job. And I think this makes sense, right? Like there's no sequence data you want to try and capture. Um, so what's list ops? Just like let me just make sure I know. Parse a sentence tree without syntactic supervision, sentence representation. So it seems like a sort of like part of speech tag like idea. Make this a bit bigger so you can read it. But it looks like list ops is a sort of like syntactic tree parsing algorithm. So these involve like some aspect of recurrence, right? Because you need to know how you've parsed something so far and to figure out how to then parse it. So there's like an implicit search. And then there's CIFAR. Okay, what's the homology data set? Protein fold prediction. Okay, so there's a protein data set. And then what's CIFAR 10 LRA? Okay, so it looks like they have the code as well. Yeah, so this is the researcher at Berkeley, Kevin Liu. He's an undergrad. Damn. Okay. We're such casual boys. Okay, so let's just make sure. So data sets, scripts, run. Remote homology. Okay, this is coming soon. Okay, so I don't know what this LRA business is about. Let's just say Cypher for now. This should be fine. All right. So what I also like I briefly read this paper offline. What I also like about it is that they give a good survey, I think, of NLP. So the transformer architecture by Vaswani in 2017, it's been useful for NLP. They also talk about like all of which in all the ways in which it's good. They give a brief survey of RNNs, and they talk about few shot classification. So few shot, RNN, transformers. Um, all right, so we hypothesize that transformers, namely the self-attention layers, can be pre-trained on a data-rich modality where data is plentiful, such as NLP, and identifies feature representations that are useful for arbitrary data sequences. Okay, so basically this is like almost like the wet dream of NLP, right? This is the wet dream of ML. Sorry, this because like I mean, yes, like you have lots of there's lots of unlabeled text in the world. There's not like images maybe a bit less, labeled images even less. So this is like certainly like a very powerful paradigm. All right, so they say we take a transformer model pre-trained on NLP data like GPT-2. Why what happened? Oh, sorry about that. Okay, so they call this model a frozen pre-trained transformer, and it works across modalities, and it achieves comparable performance to training the transformer or LSTM model despite fine-tuning only 1% of the total number of parameters of the transformer model, and none of the self-attention parameters. Additionally, uh, we find the FPT models also converge faster during training, and our results suggest that self-attention layers learned by a language model may have properties amenable. So the title of the paper is here. It's pre-trained transformers as universal computation engines. It's basically making the claim that you can use transformers on any modality, train a transformer on any modality, and then test it on any other modality. So basically, train on language, test on images. This is kind of a big deal, actually. And I made the claim earlier today that this justifies the 40 million investment into Hugging Face. Okay, so the self-attention layers learned by a language model may have properties amenable to efficient universal computation. All right, so basically, like fine tune only last a few layers, like the fully connected layers, right? Because typically, but you don't train the attention at all. So bit memory. Okay, so I'm guessing just memorize bits. List ops is a sequence of list operations. Oh, and predict the resulting output. Okay, that's fine. Okay, so far the self attention forward layers are frozen. Okay, yeah. So this is sort of to be expected, right? Like the output layer typically here is like let's say you're doing some form of classification, then this is going to be let's say you have 10 classes, then this is going to be a fully connected with 10 output classes, and then you could have like let's say a cross entropy at the very end of it, so you can actually do classification. But this is the point here is that this is sort of what you would get from, let's say, Hugging Face, right? Like the Hugging Face pre-trained. And the idea is that you would do this, and you could say just like self dot Hugging Face equals Hugging Face, and then you would say uh, basically the output layer is output is equal to fully connected of self dot Hugging Face. Like that's pretty much exactly what your code would look like. It's like absolutely nothing crazy or anything weird going on here. Okay, so let's keep going. Okay, so they use MNIST. You've seen this like image patches of like sorry digits. Sci-Far has a bit more classes. Okay, so this is long range arena where the images are converted to grayscale and flattened with a token length of 1024. This task is much more challenging than vanilla Sci-Far as models must learn patterns over significantly longer sequence length and have minimal spatial inductive bias. This seems a bit convoluted, I will say, but basically I'd call this like flat sci-fi. Okay, and so the remote homology detection, I have a video just on proteins, but the way to think about it is a protein is really just a sequence, and it's going to have like a bunch of amino acids. So like think like, I don't know, A, C, T, and stuff. So there's going to be a whole bunch of these. And then the parts that, and let's say you want to take the pairwise attention between like, let's say C and everyone else. Then you look at what's the max, and then that max will be where the fold is. So if you're interested, you can look at the Bertology paper. I think this is mostly by the Salesforce research people. I think have the clearest to understand work here. So this is Jesse Vig and Ali Madani. Just like go read their papers. I also have summarized them in my protein video, but just in case, you can just go check them out. Okay, so we're saying here that the embedding size is number of layers. Okay. So it is crucial to fine tune the output layer since we are transferring to a completely new task. Yeah, the output layer has n dimension, then d out for the weight matrix. For the base models, this comes out to 768 times 10. So 10 is the number of classes. So what's 768? Number of dimensions. Number of dimension. Oh, I see. So it's the size of the hidden layer. Okay, fine. Yeah, I mean this is obvious, right? Because like you need to turn the 768 shape into a 10 shape, right? So it's going to be 768 times 10. That's all fine so far. They're using layer normalization. So all of these guys just generally have some form of normalization that happens. Layer norm specifically is useful within the context like you don't want the like basically the output of any given layer to be much bigger than any other layer. So that's what layer norm really does. But there you can think of it as like, okay, well, why not batch norm? And it's a good question. You could use batch norms, it's fine. They probably all work. Yeah, but layer norms, like I've seen, is very popular, and the code is actually like just 2-3 lines of code, so you can go check it out in the Hugging Face repo or something. Um, so yeah, so they're saying, okay, can they transfer to different modalities? Okay, so they're saying test accuracy versus fully training transformer. Uh, Results are transcribed from figure 1. Okay. So let's see. So the LSTM seems to do really well for nothing. Doesn't do well. I find it surprising how LSTM just have like a huge like deal like struggling with XOR because like these are sort of all like good baseline models before you get to complicated stuff. Like these generally should be able to work. So let's see. So we have okay. So here with this full okay 100. And then it seems that the FPT is generally it's not always worse. So here it's better, and then here it's better. Sorry, let me do this again. So this is better, and then this is better. This is better. This is better. This is better, and then these are the same. So it's about even. Like the full one is a bit better as you would expect, but it's also much more expensive, right? So if you're to plot this with some pretty Pareto curves, or you're saying like given a certain compute budget, how much better would it be? Then obviously the FPT, like the frozen pre-trained transform, would be a lot better. And these data sets are all fairly similar. That said, I wonder like what did they train it on? Did they say? Maybe it's just like some pre-trained model they downloaded. That's what they mean. Is it Bert Large or something? Like I don't know. Like let's just say like this is a model that they've downloaded somewhere from the internet, and then this sort of probably I'll probably work fine. So I don't know Bert Large or GPT-2 or whatever, and then just fine tune it. Okay, so they actually do say. I'm sorry, yeah, I got ahead of myself. So they said okay, so they compared the performance to other base models. So like let's say random initialization, bit memory task, and then freezing the memory parameters before transferring. And then using a pre-trained vision transformer from Dosovitsky et al. Pre-trained on ImageNet 21K. Okay, that's fine. So again, let's look at this. Random seems to do pretty. Wait, I don't get this. Like, so they're randomly initializing, but then they're not training it. Oh no, no, they are fine tuning it. Okay, right. So even if it's random, it should be. Yeah, yeah. Okay, this because I thought like, how can it be better than a coin flip in this case? Anyway, guys, I see there's a lot of people watching. If you have absolutely any questions about this or anything else that I've worked on, just feel free to let me know. Um, Again, this paper I think is probably a good case study for why Hugging Face is worth a lot of money. Um, okay, while freezing a vision transform yields better improvements, pre-training on images is not uniformly better. So VIT is worse on protein classifications. Oh, I see. Interesting. And so, like, basically, here they're saying that maybe proteins are closer to NLP than it is to images. This seems a bit hand wavy, so let's just ignore this point. A random LSTM instead of the architecture and consider the raw effect of the architecture. Yeah, so again, what's better than LSTMs? Okay, so on BitXOR, the model must produce the element-wise XOR of 2-bit strings presented sequentially. Oh, interesting. So it knows like this is the beginning of the string, this is the end of the string. Okay, so you can create like almost infinite data with this, right? We talked about this. You can just have a generator that generates a whole bunch of strings, takes XORs, and then that's your data set. So that's generally a good sign. Like there's domains where you have infinite data, right? And then this is certainly very easy. You don't even need to parse anything from the internet. You can just like write a small script that does this for you. And so does the language pre-training improve compute efficiency over random initialization? I mean, if it doesn't, then it's really useless. So it seems that 4x, 10x, Lisp up. Uh, what's really bizarre about this is that the interesting ones, the improvements, not so much, right? Like, so first off, so random is faster. What do they mean by this? Oh, I see, I see. Okay, yeah. So that's a speed up. Okay, got it. So I was just confused, like, because I thought they meant a quarter, like it's a quarter of the speed, but it's 4x the speed up. Okay, my bad. I got confused there. So it seems that like generally this is true, as in using a pre-trained transformer, regardless of the modality, is faster. However, it seems for the most important data sets, this is not necessarily the case. Like let's say for sci-far, for homologies. Well, for the sequential sci-far, it seems like there's a difference, but this is also kind of a convoluted data set, so I don't know like why I would care. For MNIST, this difference seems to be substantial. And then for straight up memorization, it's a lot faster. And so it almost feels to me like for tasks that involve memory, like pre-training is king. So by that, I want to try doing yeah. So yeah. So for tasks that involve memory, it seems like pre-training is king in this regard. Let's just keep going. So does freezing the transformer prevent overfitting or underfitting? All right. So in contrast to their fully trained counterparts, they underfit the data, which lends them to further improvements by increasing model capacity. That's definitely I guess, like a half glass full way of viewing things, right? Like if your test performance is worse, you're like, oh, we underfit the data. But yeah, okay, whatever. Granted, let's just say we'll go for bigger models. My model isn't bad. I'm underfitting the data. All right, because like even the test accuracy here isn't better. Oh, but I mean, no, actually, it's like 12 more layers. Like, sorry, four times the amount of layers, and the performance is still worse. But these are fully trained on this, right? So it almost feels like we need a table that shows the actual compute time spent. Let's just say it's a very small fraction. I don't know, like less than 1%. It sounds like because they did say I think 1% of the weights is what they would fine tune. Um, well, they're also saying that it seems like the performance seems to scale monotonically with the model size. So scaling works, at least for these sizes. Uh, Again, so now they're showing the standard deviation of the parameters by layer for the pre-trained GP2 versus default initialization parameters. Default random statistics. Okay, so it's all flat line, and then the pre-trained statistics. Okay, so in this section, we investigate additionally fine-tuning the self-attention and feed-forward layers, which were previously frozen. Okay, we simply add them to the list of parameters fine-tuned without changing the optimization. Okay, so they're gonna okay, so they're really comparing three things, right? So one is pre-trained, and then fine-tune fully connected layer, and then is train, right? So this is sort of the default case, and then there's pre-train on everything, and then fine-tune on everything. So you would expect this to do better, but let's just see. I guess they're gonna say like it doesn't change that much. So the FPT, for example, and then they're saying, okay, we're gonna fine tune the fully feed forward, and then they're gonna fine tune the attention, and then they're gonna fine tune both. Okay, so if fine tune the, how does the performance get worse? This makes no sense. Like how is having more weights? But fine tuning the attention layers can lead to divergence. I mean, okay, this is making it worse. This is making it a bit better. Does this make sense? Like this doesn't make sense to me. Why would fine tuning like why? Like why would fine tuning make things diverge? Why? I guess maybe it's just like the target data set isn't as rich, I guess, is really what the issue here is. Target data set. Okay, so they also test out this trend on a bunch of other transformer models, including BERT, T5, Longformer, and GPT. Okay, and then can we train transformer by only fine-tuning the output layer? Speed ups. First, the wall clock time per epoch. Larger models have larger speed ups. Okay, so if you fine-tune the output only, then you can get like on the order, okay, 500 to 2000 x speed ups. Like this is huge, right? This is a lot, by the way. Instead of being, you know, 500 days, which is a year and a half, it's a day. So it's a big deal. But okay, granted, like so far we're saying scales number, but not in the data sets. We find CFs extremely significant and they obtain non-trivial performance, also exhibit overfitting due to lack of regularization, unlike the training uh, of the frozen transformer, dropout is not applied. I mean, yeah, because like there's not a lot of data, so they don't want to regularize things too much. But this is interesting. So I guess like let's see. So here, pre-trained. Okay, just like quickly reading. Okay, so it looks like they're detailing like a ton of related work. Let's just go through these quickly. Okay, so they said, yeah, it seems like these are useful for multiple modalities, and they talk about like images and multimodal tasks, and they talk about like Vilbert and Clip. So these are all works that we've mentioned before, and like now Dolly. So this is, I remember this is a very recent paper. It just came out this week. Um, there are also many works looking at transformers specifically in the context of in-modality transfer, such as VIT for vision, T5 for language. Okay, so so unrelated question: do you have a podcast? If yes, what is the name of it? So yeah, I do actually. So it's called Breaking Stagnation, and I typically host those on a Clubhouse. Like it's going to be the third one is happening this weekend at noon Pacific Standard Time, and it's going to be with Bharat Ramsundar, and we're going to talk about the semiconductor wars. It's going to be dope. Bharat is extremely interesting. I follow him on Substack, where he talks a lot about the semiconductor industry. So it's going to be great. It's a completely different scope, I guess, from what I would cover on my usual Twitch streams. But yeah, I'm pretty pumped about it. So the nature of computation performed by self-attention layers also has been explored by other related works, that a single transformer can be trained to perform an optimization step towards finding a stationary point. Okay, it's to first train a large model and then fine-tune on a small downstream task. A common method used to fine-tune transformers are adapter networks, which are at the fully connected residual block for each unique downstream task and also fine-tune the layer norm parameters. Okay, so I'm just gonna add a quick note here. So layer norm helps. Layer norm plus skip connection for all downstream tasks. I think this is interesting because as opposed to just having like the transformer and then the fully connected layer, you basically say, no, like I'm gonna zoom into this transformer and it has a couple pieces, and then I'm gonna add like explicit connections to the fully connected layer. So yeah, these are good tricks. I haven't thought about this for before adapter networks. Okay, global workspace theory sounds fancy. So A common technique for evaluating the embeddings learned by unsupervised models is to train a linear layer on top of the embeddings for downstream tests. Sure. We've seen this trick a lot, by the way, so far on the stream. So definitely the way you should think about fine tuning is just add a layer that has the shape that you need it to. There's a blackboard that different parts of the brain send data to, and we might consider the frozen language model as being the blackboard in the setting. Okay, reservoir computing. I did not expect this to take a turn. Okay. A random recurrent network is frozen and only the output readout layer is trained. And these models are very fast to train using similar because activations. Okay, interesting. So this is an idea where you take a random. So imagine that this part was completely randomly initialized, and then you just train the fully connected layer. And I think the reasoning here is I think there's this really old paper that I love called kitchen sink classifiers. I think this is what this is referring to, the kitchen sink classifiers. And what this paper does is it discusses how you can have completely random features for a model. And then given those random features, you can then train something like logistic regression on top of them, and you can get like really good task performance. And so the reasoning is it doesn't matter what your features are, it just matters that you're aggregating a lot of them. And as long as they're on average, like let's say better than a coin flip, or they're somewhat instructive, I mean, maybe you could prune a couple with PCA or something, or just looking at the average weights of for each one. There's like a pretty good way of, and it's like an interesting intuition for why like these random architectures work. I think also Hard Maru had a paper on random architectures. So just pick a random architecture and then train that random architecture, and it's pretty good. And I've also seen the opposite, which is you take a specific architecture but random weights, and it also tends to be really good. So I think this is what this is referring to here with the reservoir computing. All right, so we propose transferring a pre-trained transformer. They could achieve performance for transformers fully trained on downstream tasks without having to fine-tune the self-attention and the feed-forward layers, relying solely on frozen parameters from the language model. Okay, that's great. And this work can be a good foundation and explore frozen pre-trained model in situations like reinforcement learning. There's also some concerns around using pre-trained models for bias, and this is an active area of research. Uh, Representative data sets from one, which might switch investigation as well. Okay, interesting. So let's take a quick look at the appendix. There's like a long list of references here. And I actually like here they had like a good summary of attention, for example. Like this is extended to multi-head attention. So this is just the single weights, a residual connection, just connect the inputs with the outputs of the attention layer. Okay, that's great. And then they also talk about positional embeddings here. This is just like a way because you can think of an attention matrix like it doesn't know what the order of stuff is, so you just add it to the representation. Uh, this is layer norm, and then a pre-training objective. So here it looks like yeah, they're just talking about given the previous I minus one words of a sequence, predict the next word. So this is what this is what's called autoregressive, as in like you're reading an input from left to right. Not everything is like this in language. Like there's, I mean, because when I read stuff, I don't necessarily understand it from left to right. I sort of parse all over actually. Then they briefly talk about the experimental setup. So they use Atom, so nothing crazy there. They use a learning rate of 10 to the minus 3 with no scheduling. Interesting that they use no scheduling. The largest batch size that can fit between 2 and 16 without gradient accumulation, and models are trained to communicate. Okay, it converges. Okay, great. So basically, I think this was actually a surprisingly simple paper to understand. And just going over it. So again, this was pre-trained transformers as universal computation engines by a bunch of star researchers, and they showed how a transformer trained on a modality like, let's say, language can do pretty well on images and vice versa. They compare this to a bunch of other schemes to which people usually do transfer learning, from like retraining everything, training from scratch, freezing a couple of the layers, freezing only the last layer, training only the attention. And so this is like a promising research direction, and I think it justifies the need to centralize model development more, which would increase the valuation of companies like Facebook or Huggingface, because then if they train stuff and then you fine tune it off of their data sets, that's very scalable for them, and it's good for you as a consumer because you don't need to spend a lot of money training these things from scratch. So thank you everyone. If you enjoyed this, please make sure to subscribe and like this video. Let me know that you like it. And I do have a couple of bunch of videos coming up next. I think next week I'm giving two talks. One is going to be on how to learn ML, and the other is expanding on the ideas from my blog post on the Great Stagnation. I'm also doing a clubhouse this weekend on with Bharath Ram Sundar talking about the semiconductor wars. And I think my next Twitch stream is going to be on distributed learning with PyTorch. So I'm going to be going over all of the ways in which this is done. So I hope you enjoy it. I certainly did. Thank you, everyone, and I'll see you next time.